Hello everyone. We'll still get started in just a minute or so. Hopefully people can hear me okay and now see me okay as well. And then today we are going to be doing some counting and probability problems for upper elementary and middle school students. So a lot of maybe middle school level questions, and I know a lot of times people have a little bit more difficulty with some of these counting and probability questions as well. But that'll be kind of good to practice some of those things and still kind of talk about some of those different types of problems that we have that way too. So to introduce myself again, I know a lot of people have seen some previous videos and stuff, but I am Mr. John from Areteem Institute, and I'm excited to be working with everyone and kind of solving some problems today as well. So as a little bit of an introduction to get started here, right? We have a couple of just warm-up questions here to talk about real quickly. So these are both kind of from elementary, upper elementary kind of level problems here. And we'll talk in a second about some strategies for counting and probability questions. But of course, with any math question, you want to start by reading everything carefully. So as soon as we kind of start reading the problem, we have at the Smoothie Emporium, a customer can buy a small or large smoothie. So I want to just start kind of highlighting that right away. So we have one possibility is a small. Then do they give us information about small? For small smoothies, they get to choose one fruit. So that's kind of what we have here then. For these small smoothies, they get to choose up to one fruit there. And for large smoothies, they get to choose up to two fruits. So again, reading this is very important as we're setting up the problem here. Now, there are 5 different fruits available. That's another important piece of information, and we want to know how many different smoothies there are in total that the people could buy. Right, so if we're kind of thinking about the question, we want to know the total number of smoothies that people kind of think about. Initial tip, is we're kind of moving for some of these problems as well, What's a good way to get started on these things? Well, think about you're the customer yourself, What kind of choices do we need to make? And a natural first choice we need to decide here is either we order a small smoothie, So that's definitely one scenario that can happen. Or we can order a large smoothie, So these are two kind of definite scenarios that we need to deal with here, One scenario for small and a different scenario for large in this case. And so then we have, okay, what happens in each of those scenarios? We're going to talk about this a little bit more in a second, but if you list them out or write them out, then we want to add some things together. So, what choice do you have for the small smoothie? Well, if you decide to order a small smoothie, you just get to choose the fruit. So there are just 5 different small smoothies available. Then we have to be a little bit careful for the large. So I want you to think about what might be worrying for the large case, Why might we need to kind of worry about this a little bit more than the other scenarios there? So if we have the large fruit, large smoothie, what can we kind of do in that case? Well, one scenario is just we bought the same one we bought for the small, except in a large, So there's just one identical scenario for the large, where we just have 5, So this would be if we have kind of one fruit as well. Remember there we have kind of the 1 or 2 possibilities in that case. Now, we're going to talk about some tricks and things like this in a second, right? For how many ways we can have two fruits, right? Two different fruits. And so maybe for now, let's think about it this way. So for now, I want to kind of think about it. If you have the first fruit, that can be paired with any of the four other fruits, right? So maybe you want strawberry and then any other of the four things, right? Now, the second fruit that you have there, right? The second fruit, we already paired it with one of the fruits, so it could be paired with three other ones there, right? So in this case, we're going to have 4 plus 3 plus 2 plus 1. And a lot of you, if you're kind of thinking about more advanced ways of kind of doing that, we'll see that in a second as well, right? There's 5 fruits with or 5 large with one fruit, and then 10 with 2 different fruits. So all together, we have 10 different large smoothies. That's exactly right. Thanks for sharing that in the chat. And so we always want to just be careful, or not necessarily careful, but clear about a final answer, right? So our final answer is 5 plus 10 is 15, right? So this is the total number of smoothies we have at the end. That's exactly kind of right in this case. So that's a good one, kind of warm up here with just logical thinking. So one of the takeaways for our first problem, you just want to make sure you're thinking carefully about the problem. Okay, I can try to turn up the volume a little bit. That's kind of okay as well. So yeah, let me know if kind of hearing is a little bit better if we kind of do that as well. And kind of let me know if that helps or not too. So I turned it up a little bit on my end, so hopefully you can hear a little bit better, and then otherwise we'll see if we can fix it later on too. Okay, now the other warm-up question is actually a little bit easier than this one, but I still want to kind of quickly go through it there. This is kind of our warm-up probability question. So Piper writes out all the factors of 100. So, right, we actually were nice to you. We listed them all out right here, right? 1, 2, 4, 5, 10, 20, 25, 50, 100. So a good natural question is, so how many of these factors are there in total? So, right, you guys can think about that, and I'll label that in a second. But then, right, if we're reading the rest of the question then, we have these factors in total, and then Piper is randomly choosing one of these factors. So, right, let me just write them out maybe again down here, right? And as you guys are kind of saying, how many of these total factors am I writing out? I'm writing out 10 of these in all, right? So let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9. And yep, sorry, 9 in total, right? Not 10, right? So 9 in total here. Now, what kind of is what we're looking at? So some people are talking about kind of 2/3 or things like that. So then we want to kind of highlight the ones which are factors of 40, right? So which are also factors of 40. Remember, these are just numbers that evenly divide into 40. We'll talk a little bit more about those in general tomorrow, right? But 1, 2, 4, 5, all of those work, right? 10, 20, does 25 work? No. Does 50 work? No. Does 100 work? Definitely no, right? So there are 6 of these, right? So we have 6 in this case as well. So how do we turn this into kind of our ratio, our probability from the end then, right? Right, remember here then at the end we just do the ratio. So the probability is going to be equal to 6 divided by 9, the number of ways we want, divided by total. And so everyone mentioning in chat the 2/3, that kind of is perfect that way as well. Okay, so that's kind of great here too. So what are the basic kind of knowledge points? We've already talked about some of these, right? But I just want to summarize a little bit here as well, right? So you want to, of course, read the question carefully. And especially for the kind of counting and probability questions, think about the information the problem gives you, right? So we have things like, okay, how many small smoothies, how many large smoothies. Sometimes we need to make assumptions as well, right? We'll see some problems like that in a second. We'll be talking about a race. We might need to assume that there are no ties, right? Or that everybody finishes the race, right? There are kind of just basic real world knowledge pieces that you want to bring into play there as well, right? Certain scenarios have order matters, certain other scenarios have order does not matter, right? So those are some things you want to kind of keep in mind when you're talking about these. Along with the order matters, not matters, can we have repetitions? Can objects be identical or not? These are all important questions that you want to be asking. So these are a little bit different than a geometry question or an algebra question because they might not just explicitly tell you anymore, right? A lot of the times for a geometry question, the problem will tell you you have an isosceles triangle, wherein kind of a combinatorics question, a counting and probability question, you might need to use kind of real world knowledge to tell you more information about the setup there. Okay, so what are our two main rules? So actually all of counting comes from two very, very basic rules, right? These are kind of asking and answering two very important questions, right? When do we add? That is one important question, of course. And right then, when do we multiply? Right, so that's kind of important to kind of think about there as well, right? So we have the two scenarios, when do we add, when do we multiply as well. Okay, so that's kind of the stuff here too, right? So when do we add? This is when we have cases, right? So if we're kind of breaking down a task, right? Either you have a small or a large, right? That's exactly what we did before. We added those things together. And I really like thinking about these with key words kind of there as well, right? So, or, right? So here, if we have the or in that case, we oftentimes add. If we're talking about multiplying, this is often going to be an and or a then, right? So if we have one thing happening and then we make another picture kind of that way as well, that's kind of how it's going to be going that way as well. Okay, so that's kind of good that way as well, right? So these are kind of the two very, very basic rules. Now, what are the different things we can do then, right? Of course, as you're doing more of these questions, a lot of you guys might already know some of these things, but I want to do the real quick kind of example here. So how many people kind of could run in a race? Let's say we have 10 people running in a race. Of course, no ties, nothing like that here as well. So how many different ways can they finish, right? So of course, for kind of things like this, we can actually just use the product rule. We need to decide who could win the race. Well, there are 10 choices for who wins the race. Well, then who gets second, right? Well, there are 9 choices. Who gets third? There are 8, right? Who gets fourth, 7, etc. Now, a lot of you guys are saying, right, and a lot of you guys probably already know better ways of writing this down as well. So that's one of the kind of things we want to kind of think about and make sure we're kind of okay with here as well. So of course this is right. We don't need anything other than the product rule to do this, but that doesn't mean this is the most efficient way of writing down the answer or of knowing the answer, right? So this number is a big number, 3628800. And right, as people are saying in chat, that's good, right? We have an excited 10 as our answer here, right? Of course, no, this isn't an excited 10. This is, right, 10 factorial, right? So 10 factorial here is kind of our new notation that we want to just make sure if we're not already okay with that, right, we know that that is what it is as well. Now, is anything different if we start talking about gold, silver, bronze? Well, in fact, that's just 3 of the people that matter, right? We only care then about the first 3 places, right? So then in that case, we have just 10 times 9 times 8. Okay, and so good, right? This is just 720. That's perfect. And now again, you want to be able to write this, okay, what if we had 200 people and we wanted to give out 22 medals? Is that question really any harder? No. Is that more annoying to write down? Maybe, right? And so that's why we want to get comfortable with these factorials. So this is very similar to the previous problem, right? We have a 10 factorial here, except we're missing the 7 factorial, right? So this is 10 factorial, but missing 7 and down. So how do we fix that? Well, you can exactly just divide by a 10 factorial, right? Yeah, so this is why these things, right, the patterns are going to be very common. And I'll summarize this quick on the next kind of slides as well. So yeah, 10 factorial over 7 factorial isn't helpful here, but it's kind of helpful in that scenario like I was mentioning, right? What if we have, 200 people and 22 medals? Then notation like this at least lets you to write down some sort of answer. Now, why is this groups of people different? What happens in the groups scenario that's different from the other ones, right? Here we don't care about who gets which medal, right? So the key here is, right, who gets gold, silver, bronze, doesn't matter. So that's kind of our difference here. So should our answer be larger or smaller than the previous one? Pretty clearly it should be smaller, right? We want this number to be now less because we don't care who gets gold, silver, or bronze. But if I give you a group of people, how many ways could you give out the gold, silver, and bronze, right? That would just be 3 ways to pick the gold, 2 ways for the bronze, or sorry, 2 ways for the silver, and 1 way for the bronze, right? So if we wanted just to write our answer here, this would be the previous answer divided by 6. Yeah, people are saying 6, right? Why 6? This is the 3 times the 2 times the 1, right? So of course we have an answer in this case, right? 720 divided by 6 is equal to 120. But also, again, just as some preview, we want to start getting this comfortable with factorials. Now, those of you who might be a little bit advanced in chat, what are we really talking about on this page? What are we really kind of giving examples of when we have this kind of easy question to start with here? What kind of really are we talking about when we have stuff like 10 factorial over 7 factorial, right? 10 factorial over 7 factorial, 3 factorial, things like that, right? So we have kind of things called, yeah, we haven't said the actual names, but you guys are on the right track, right? We have permutations here and combinations, right? These scenarios come up so often, they have a special name associated with them. I want to stress this is nothing more than the product rule or the reverse, right? At multiplying when you divide, that's really all product rule. But these things come up so often, it's very useful to have names for them and just have notations for them to write down immediately. Right, so what did we want? We had in the last problem 10 people. We maybe wanted 3 of them. So if the order matters, we have this permutation. N factorial divided by n minus k factorial there, right? So that's kind of what we have in that case there. Okay, so right here, our notation and kind of verbiage, vocabulary, permutation here is kind of rearranging all the objects, n factorial divided by n minus k. And somebody already mentioned the other one in chat as well here which is a combination, right? So here this is when the order does not matter. We have our n factorial divided by k factorial times n minus k factorial. And especially as you do more and more of these problems, you'll see these written out in terms of kind of parentheses and like a fraction, but no fraction in between, right? So we're not going to really do this too much today, but this would be called kind of, you would read this as n choose k, or kind of this is called a binomial coefficient. Okay, so that's kind of what we have in this case. Okay, so as we're kind of moving on to the next question then, right, we have basic probability as well, right? So we already did our warm-up question with probability, but I really want to just highlight this formula of, right, want divided by total, right? So the probability is the total number of outcomes in our denominator and the number of outcomes we want in the numerator. And there's different ways to approach this, different kind of reasonings we can do with that. But that's kind of the general idea still that way as well. Okay. So, once again, let me give a quick pitch here, right? All of these problems are coming from ZIML problems, right? You can check out the app or ziml.areteam.org, right? We have new sample kind of contests right now, right? We actually have a monthly compete or try a sample contest for a chance to win free monthly contests the rest of the year. Right, that's kind of going on right now a little bit. So, right, you can look more on our YouTube page or other social medias and stuff like that there. But kind of that will be one other way to kind of participate there. But for today at least, right, we are kind of going through some stuff here in terms of some practice problems in this case. So remember, a lot of these are kind of just logical thinking. The most important thing is how do we break down a problem piece by piece here? So as part of her practice, Jane needs to jump 5 meters. She can make jumps of 1 meter or 2 meters long, right? So, right, how many different ways can she jump the 5 meters? Now, this problem isn't difficult, right? But the one slight thing we need to worry about, right? So the one caution here, there are different combinations of jumps that work, right? So that's kind of what we have in this case, right? So that's the only thing I would say you need to be a little bit worried about here. So, right, different combos of these jumps that work. What do I mean by that? What I mean by that is you can put together different kind of ones that will kind of be working, right? So what is kind of the easiest or kind of most straightforward way to do this, right? Maybe it's a little bit boring, right? But Jane could do, okay, a 1 meter jump, a 1 meter jump, a 1 meter jump, etc. She can just do 5 1 meter jumps here, right? So this would be kind of 5 1 meter jump that one. So, right, that would definitely work here. Now, what are some other possibilities for this, right? She could, of course, do a 2 meter jump and some 1 meter jumps, right? So we could have 3 1 meter jump and 1 2 meter jump. What do we need to be a little bit careful with in this scenario? What kind of is the worry we have here, right? The issue is, right, the 2 meter jump can take place anywhere, right? So what do I kind of mean by that here, right? We have different possibilities, right? We could have 1 plus 1 plus 1 plus 2, or 1 plus 1 plus 2 plus 1, or 1 plus 2 plus 1 plus 1, or 2 plus 1 plus 1 plus 1, right? And since this is kind of the basic problem, right, I think it's just easiest to list them out like that there, especially for explanation purposes, right? And we have the same kind of thing for the last case, right? Are there some tricks for kind of how you count these? Well, sure, right? Here, if we have the 3 jumps, we know kind of that the 1 meter jump is the first jump, the second jump, or the third jump, right? So we have kind of different tricks for counting these. But regardless, it's pretty easy to see the number of cases. 1 way, 4 ways, 3 ways. What do we do with all of these, right? This is or, right? Or. So what do we do when we have or? We have plus, right? So there are 8 ways in total here. So that kind of is good to be thinking about as well. The other thing I want to quickly mention here is that, right, notice that we're also thinking of summing up to 5, right? So there's all kinds of these connections you want to start getting comfortable with, right? What are the different ways of thinking about the same problem to kind of go through it there? Okay, so let's do another question about people and arrangements and racing a little bit here. But there's another trick that's kind of good to think about here. So Sunnyvale Middle School organized a race for their students. 3 girls and 6 boys participated in the 4th grade race. If no girl finished the race right after another girl, in how many different ways could the students have finished the race? So, right, we have now boys and girls. Now, which do we think is easier to deal with? Is it going to be easier to try to arrange the boys or the girls? Right? So, one way to do this, right, is to just sometimes you want to just be lazy and do the easy thing first. So, blah, 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 no girl finishes right after another girl. Wait, so that means the girls have to be separated, right? We have some restrictions on where the girls are. I would actually say it's because of that, it's easier probably to arrange the boys, right? The boys have no restrictions, right? Boys, because they have no restrictions. And so actually this is exactly one of the things we talked about. There is just 6 factorial ways to arrange the boys, right? So this is kind of, maybe if you think about it differently, it might be easier for you to arrange the girls first. That's perfectly fine if you want to kind of start thinking about where the girls go and things like that. But, right, in this case, right, we can say, okay, the boys have no restrictions. There are 6 factorial ways to arrange them. Now, remember I said we had to make some assumptions, right? What are we assuming here about the people? The people are all different, right? Right? So they're all kind of different boys in this case. Do we care about the order of a race? Well, yeah. If you're running in this race, you want to win or you want to beat your competitor, right? Things like that, right? So there are 6 factorial ways in total for arranging these boys. So yeah, let me know if there's any issues about that, but we've already arranged the boys. So kind of for now, I just want to think about, okay, what are the kind of boys gonna look like in this race, right? So we have the 6 boys that are finishing in some order, right? There are 6 factorial ways, 720 ways for the boys there. Now, where can the girls go, right? Do we know that the boys beat the girls or the girls beat the boys or things like that? No, right? We don't know any of that. So they could kind of go anywhere in these kind of orderings, right? So one thing though we have to worry about, right? So the girls can be anywhere, except, right, not next to each other. So actually though, right, this is one of our tricks. Sometimes you'll see this as kind of called a spacing trick, right? There are kind of 7 of these spaces, right? There are 7 spots between the boys, right? And each girl could go in these spots. And we just have to make sure that the girls can't go in the same spot, right? So girls can be in any spot, but no 2 girls in one spot. Okay. Okay, right? So the girls can be in any of these spots, but not 2 of them in the same spot. So what about the first girl? First girl could be in any of the 7 spots. Second girl, now there are 6 remaining. And then there are 5 remaining. So this is just 210 in this case, right? So this is 720 and 210. So is our final answer here then 930? Is that what we have as our final answer in this case? Right? We want to be careful. We want to be thinking about how do we put things together. We just saw a bunch of problems where we put stuff together by adding, but that is not what we're doing here, right? This is a multiplying situation, right? we have the number of ways to do the boys and then the number of ways to do the girls. So we need to multiply these things together. And kind of as shared in chat a little while ago, right, you can do 72 times 21 and then add 2 zeros. And so our final answer here is 151,200 in this case. So that's kind of what we have here as our final answer here. Okay, so let's do kind of a couple more problems. Some of these we can do a little bit more quickly, and I want to make sure we have some other kind of situations that we're dealing with as well. So let's look at a probability question next. So a bag contains red, blue, and green balls. 60% of the balls are red, 15% of the balls are blue, and the rest are green. Tim grabs a ball and writes down its color before placing it back into the bag. Then he repeats the process 2 more times. And we then have what's the probability he grabs 2 green balls and then 1 red ball. So pretty clearly here, we have an order, right? And we can start looking out for our key words here, right? Green ball and a green ball and then a red ball, right? So we're looking for the probability here that we have a green ball and then we have a green ball and then we have a red ball like that. So when do we multiply, right? When we're doing things in order. We have a first step, and then we have a second step, and then we have a third step here. So what's kind of the first thing we need to be a little bit careful about, or a little bit kind of think about here? Well, how many balls are there, right? You could say to me, Mr. John, you told me earlier probability is like want divided by total, right? How can I do that if I don't know how many kind of balls there are there? Well, in fact, the problem is actually easier than that, right? Because what is it actually telling you? The problem is, in a sense, telling you some of the answers right away. So when we say here that 60% of the balls are green, or sorry, 60% are red, right? So what is that telling us? That's kind of already telling us the probability, right? So if 60% of them are red, the probability that you get a red ball is 60%, or right, you could write that as 6 over 10, or this is 3 over 5. And you'll kind of see why I'm writing it in kind of a little bit weird of way in a second. Right, and we can do the same thing here for blue. 15% of the balls are blue. And so then we have the same kind of scenario right there. Whoops, and so let me use blue here. And so as I'm typing this out as well, right, in chat, if you guys could tell me, right, the natural next question is, well, how many of them are green, right? How do we figure out the green scenario in this case? So here we have kind of 15 over 100. So we could divide by 5. We have then 3/20ths in this case, right? Of course, though, our simplified versions aren't always super important. So we then know that the rest are green. What does the rest mean in this place? Well, right, I know a lot of the times we're used to percentages and stuff like that, right? This isn't like a test at school where maybe you have a extra credit and you can get more than 100% or kind of things like that. Right, so this has to be the remaining percentage, right? So, right, we have 100% minus 60% minus 15%, right? So what is left over then here, right? We just have 25% equals 25 over 100 equals 1/4. Okay, now let me take a time here for some comments and stuff here, right? How did we do percentages like this a lot of the times in the word problems, right? If you watched my video on word problems, a lot of times we just assumed, right? So that would definitely work in this case as well, right? If these percentages are a little bit confusing or something like that, right? It's perfectly fine, right? You can definitely, right, assume there are 100 balls, right? Or 20 balls, etc. Right? You might be a little bit, need to be a little careful to make sure you don't have fractions or things like that. Yeah, but if you're a little confused by the 60%, 15%, or just maybe not even confused, but don't want to think about it that way, right? Notice that this is equivalent to saying, okay, 60 green, 15 blue, so the other 25 are green, and then we have exactly the numbers we need there. So if we do this kind of in the simplified versions of the fractions then, we now have to multiply our probabilities. And just be careful, right? Be careful what we're multiplying here. So we have green, there's a 1/4 chance. Now, here's where it's important that we're placing the ball back in the bag, right? That means this probability doesn't change, right? So these probabilities don't change because the ball is going back in the bag. Right, so that's kind of important to do and kind of think about here. As an extra question in chat really quickly, could you do this if you didn't know that the ball was put back each time? Is the question possible if we don't have that information? So as I'm kind of multiplying these out, right, nothing cancels, unfortunately, right? We have then 4 times 5 is 20, times 4 is 80, so we have 3 over 80. So actually here, right, so let me just finish this, I guess, quickly, right? This is our final answer here. In fact, the question is impossible if we don't tell you that the ball is placed back into the bag each time. So that's a little bit of things here, right? So impossible to answer if we don't know the ball is put back. Why is that? Of course, if you knew the numbers of balls, that would be easy, right? If there actually were 100 balls, you could easily answer this question whether we put the ball back or not. But the percentage would change things if we kind of were not putting the balls back, right? If you have like 1,000 balls, getting rid of one of the red balls or one of the blue balls, let me say, doesn't really matter all that much. But if you have 20 balls, right, all of a sudden if a blue ball is gone or a green ball is gone, that changes the probability much, much more. So that's why we need to be a little bit careful in terms of kind of putting the ball back, and we need to kind of know how to put the ball back in this case. Okay, so let's do 2 more questions quick, and let's just kind of practice. So these questions are a little bit trickier, but a little bit easier if you know some of the tricks. So that's why I want to just kind of do these a little bit quickly, just to kind of show that when we're putting this information together, things can work out pretty nicely, right? So reading the question here, there are 10 8th graders, 10 7th graders, 10 6th graders. So 10 8th graders, and then we need a group of 6 captains, but we need 3 8th graders. So, right, so 10 8th graders, we need 3 for captains. And hopefully everybody sees that this kind of exact same thing is going to be true with slightly different numbers for the 7th graders and the 6th graders, right? So if we kind of type these out as well, right? So there are 10 7th graders, and we're going to need 2 of them for captains. And likewise, we need 1 of the 10 for the last grade here. Now, this should remind us exactly of what? This should remind us exactly of our permutations and combinations examples, right? Because this is kind of exactly here. We have n objects, right? We want 3 of them, or 2 of them, or 1 of them, right? These are exactly our permutations or combinations. Now, which one of them is it, right? So this is the same setup as permutations and combinations. We want combinations, right? Because order doesn't matter. How do you know the order doesn't matter? Well, here actually the problem tells you that the order doesn't matter. But in general, right, if you're picking a group, kind of order doesn't matter that way much as well, right? So if we do these then one at a time, 8th graders, there are 10 8th graders, we need 3 of them, right? So just quickly here, and maybe this will actually be the last one we do. If you start kind of writing this out, you'll have 10 times 9 times 8. The 7, 6, 5, those all cancel. So we have times a 3, 2, 1 here. And so then if you multiply this out, you will get 120, confirming the answer in chat, right? So that's good to see as well. Then 10 choose 2. This is a good pattern you want to kind of recognize as well. We have 10 times 9 divided by 2. So this is just 45. And then lastly, but not least, right, the 6th graders, they only get 1 of the 6th graders, unfortunately for them. 10 choose 1. Logically speaking, 10 choose 1 should just be 10, right? You can double check the formula there yourself, right? That's always kind of good to double check and see if the logic makes sense with the actual formulas, right? Then final answer here is of course a multiply, right? We multiply all of these things together, and this gives us a final answer of 54,000 in this case, right? So we have kind of 90 times 6 and then some zeros there as well. So this kind of is what we have as our final answer for the problem here too. Okay, so I think that will be kind of a good place to kind of call it for right now. Let me go back to here the ZIML page again, right? So want to kind of recommend everybody checks that out. So we kind of have the ziml.areteam.org kind of stuff there, right? Like I said, there's some giveaways and stuff going on there as well, right? We have one more live session tomorrow from 10:30 a.m. to 11:15 on number theory topics. So kind of similar to, right, the today a little bit of mix upper elementary, but then some middle school stuff. So I hope to see some of you guys there again as well. As usual, kind of I enjoyed working with everybody. So thank you guys all for spending a little time with me. And I will also end with my usual pitch here as well. Please, everybody, be safe, wash your hands, right? Try to stay healthy. Try to help keep other people stay healthy as well. I know a lot of you guys are not under that much risk, but you can do your part to help your parents, your grandparents, aunts, uncles, right? Other people like that in the community as well. So I will kind of say goodbye to everyone for now. And I'll see you guys later on then. So have a good rest of the day. Goodbye.